what we're doing in this chapter is we're analyzing graphs of functions, and we're using the derivative and the second derivative to help us analyze these graphs. And then one thing we need to do, and so I was thinking about this problem over the weekend. There was one kind of like this in your homework. I'd like to try to address this. I'm going to do this. 4x over 2x squared minus 5x. Wow. All right. So right off the bat, the function is a quotient, and just to do the first derivative will be a challenge. You got a little quotient rule. If you're going to try to do a second derivative, that might be another quotient rule. Who knows? So just right off the bat, this problem is a lot more work. But the other thing this problem does is it brings up the idea of, before we do derivatives and work on that, it brings up the idea of we're trying to analyze these functions, and sometimes these functions are full of asymptotes. And so maybe you recall from your pre-calculus days what kind of asymptotes you have here and what's going on here, but I'm going to remind you about asymptotes. First of all, there's some vertical asymptotes. Vertical asymptotes happen when? When do vertical asymptotes happen? Do you know? Specifically, we'll work on this one, but in general, when do we get vertical asymptotes? When the function's undefined. Although we learned when we were dealing with limits that sometimes those undefined places are holes. Damn it. Hang on a second. Can I change this problem? I'm just going to add a little -1 right there, if you don't mind. I didn't want to have a hole. I think I just had a hole there. But now I fixed that, I think. All right, so when the function's undefined, we get these holes or we get these vertical asymptotes. Mostly, I think they're vertical asymptotes, unless, if you remember, that factor cancels in the numerator and the denominator. That's kind of what made it a hole, if that factor cancels away. But to find vertical asymptotes, basically, when does the denominator equal 0, right? When is it undefined, right? So you factor out a 2x, or no, you factor out an x. You're left with 2x minus 5. By the way, just a couple minutes ago, that x would have canceled, and that would have been a hole. So now I don't have that. Now I think I got two places. I think I got x equals 0, and I think I got x equals 5/2. How are you guys doing? You okay? And I think those are vertical asymptotes. They're places where the function is undefined. They're vertical asymptotes, and they're not holes. If you could cancel one of these away with somebody in the numerator, then that was called a hole. Yes, Carlos?
Basically, happens if it's undefined in both the original and the derived equation.
Yeah, we haven't gotten there yet. So when the function is undefined and it doesn't cancel away in the numerator, those are vertical asymptotes. So that's old pre-calculus, college algebra stuff I'm just reminding you of. You should remember that. Hey, do you remember the rule for horizontal asymptotes? Do you remember the rule for horizontal asymptotes? From pre-calculus and college algebra and blah, 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 from kindergarten. From kindergarten, do you remember the rule for horizontal asymptotes?
On the other same degree.
Well, yeah, it's quite a bit longer sentence than that, but you're onto something. You're right. When the numerator has a lesser degree than the denominator, it's automatically a horizontal asymptote at y equals 0. Automatically. When they have the same degree, then it's a ratio of those leading coefficients. When they have the same degree, then it's a ratio of those leading coefficients. That's the rules for horizontal asymptotes. I just quickly reminded you of those. That's it. That's the only two rules. When the numerator has a lesser degree than the denominator, it's automatically y equals 0. If they have the same degree, then it's the ratio of leading coefficients. The ratio of leading coefficients. Y equals the ratio of leading coefficients. I could write all that down, like fancy rules for you. You want me to write that down for you? I mean, I did when I did college algebra for pre-calculus. I wrote those rules down. That's it. Your book in section 4.5, in your calculus book, in section 4.5, they kind of address asymptotes. They kind of remind you of this, and they remind you of horizontal asymptotes, but they approach them differently. I just told you the 2 rules for horizontal asymptotes, and the 2 rules I just told you are very algebraic rules. In calculus, they tell you, and this is true, by the way, maybe you should know this, that you get a horizontal asymptote when you ask this question: what is the limit of the function as x goes to infinity? Because when x goes way the hell out to infinity, is it approaching a horizontal asymptote or not? I mean, that horizontal asymptotes are only asymptotes when x heads to infinity or negative infinity. I mean, that's when the horizontal asymptote comes into play, when x gets large or very negatively large. So there's a big discussion in 4.5 about these limits that go to infinity. I'm not sure how much of these limits I want to discuss. I want you to know about horizontal asymptotes, though. And maybe I'll get back to these limits. But with that, but what I am doing is what I'm trying to do is take a derivative, maybe a second derivative, and look for critical numbers and inflection points. And you with me? That's where I'm trying to go. But I'm actually pausing and saying, hold on a minute. Sometimes you got to pause at the beginning of the problem and check out the asymptote situation. We haven't done much of that because we haven't had much asymptotes involved. But with these kind of functions, these rational functions, you can have vertical asymptotes, you can have horizontal asymptotes. Let's take a look at this graph. Well, I don't know the graph yet, but I do know that there is a horizontal asymptote at y equals 0. There's an asymptote here at y equals 0. There's an asymptote at x equals 0, a vertical asymptote at x equals 0, and another one at x equals 5/2, which is 1, 2, 3, 2.5. 5/2 is 2.5. Cool. And then the graph lives between these areas, and maybe it has mins and maxes, maybe it has certain concavity, maybe it's increasing, decrease. I mean, in order to analyze all that, I think I'll try to do a derivative. But the game just got tougher because it's a quotient rule. Let's try it. The derivative, please. The derivative is quotient rule, derivative of the top. 4. That's awesome. Write down the bottom, 2x squared minus 5x, minus the top, which is 4x minus 1, and then the derivative of the bottom, 4x minus 5, okay, all over the denominator squared, Wow, oops. Okay. The way to clean this up, because now we're looking for critical numbers, the way to clean this up is to distribute and collect like terms in the numerator. That's how these quotient rules always clean up. You clean up their numerator and you practically got them clean. You do not, I've seen students do this, but you do not cancel this. That's bad algebra. It doesn't cancel like that because it's added or subtracted to something else. So I'm not canceling anything, but I am going to distribute and clean that up. That's an 8x squared minus 20x, 16x squared, negative 16x squared, negative 24x plus 24x plus 5 minus 5. Wow. I FOILed that out and I distributed the negative sign all in one move. I learned that in kindergarten. I'm going to collect like terms. What do I got? I got a negative 8x squared, a positive 4x, and a negative 5. Wow, you guys. Who made up this problem? Got to complain to the problem maker-upper. You guys okay? I got my derivative. And I'm interested in, this is my derivative. It's all cleaned up, and of course, I'm looking for critical numbers. So I ask myself, when is it 0? Well, when is it 0? When that numerator equals 0. I guess I should do a quadratic formula. Unless it factors some fancy way. I don't think so. I'm going to do the quadratic formula. On your mark, get set, go. Well, nothing wrong with a Monday morning quadratic formula, right? Negative b plus or minus the square root of b squared. That's a 16. Minus 4 times a times c. That's pretty interesting. You know what? All over 2a. I'm not going to work too hard on this. I think this is headed toward imaginary answers here. That's 16 minus... It's going to be negative. That's going to be a negative huge number. I'm done. These are imaginary answers, not real answers. So in other words, when does it equal 0? Never. In the real number system, never. Well, that's interesting. That means I got no critical numbers. I mean, maybe I got no critical numbers. Maybe I got no maxes and mins. Right, I got no critical numbers. Yes, Carlos?
But you said that critical numbers, it's not just when it equals 0, but also when it's undefined.
Okay, thank you. Good, Carlos. Thank you. So, thank you. So, when I take a derivative, you're right, I'm interested in two things. When does it equal 0? And we found out that's never. And when is it undefined? You're right, those are also critical numbers. But look at it. When is it undefined? It's the same denominator, except that it's squared. It's the same denominator you had in the original function. When was the original function undefined? At these places. And they were vertical asymptotes. So guess when this is going to be undefined? The same places. But let me say something. They're not really critical numbers. They're not critical numbers because if you remember our definition of critical numbers, they had to be defined in the original function. So if you have something that's undefined in the original function, they're going to show up as undefined in the derivative. Guarantee you. We haven't practiced much of this, but this is truth. If you got something undefined in the original function, it will show up as undefined in the derivative. So, and back in the original function, they're not points, they're not mins and maxes. What are they? They're vertical asymptotes. So they're not critical numbers. So I really don't have any critical numbers. But you know what I'm going to do? I'm going to go ahead and do a number line right here. But I don't have any critical numbers. So who do I put on the number? I don't have any critical numbers to put on the number line. Well, so I haven't told you this yet, but I'm telling it to you today. Hang on a second, Carlos. If you have these undefined places in the original function, when you have these vertical asymptotes, listen to me. I know they're not critical numbers. We just argued that, hey, they're not really critical numbers. But I want to put them on the number line anyway. And I want to test around them. I know they're not critical numbers. They're not going to be mins and maxes. But I'm going to test around them. I guess I'm testing for increasing and decreasing. That's what I want to do. I want to test around these guys for increasing and decreasing. They're not critical numbers. They're not going to end up as mins and maxes. We know that. But I need them on my number line to test around them. And here's why. Look, when you have vertical asymptotes, don't they just naturally split the graph into 3 pieces? I mean, that's what asymptotes do. They split the graph into 2 pieces or 3 pieces or 4 or 5 pieces. I mean, with these 2 vertical asymptotes, this graph is going to be split into 3 pieces, and I want to analyze the derivative of each piece. There's no critical numbers, but I want to analyze all 3 pieces for increasing and decreasing. So here I go. Pick something down here on the left of 0. -1. Where do you plug it?
Into the derivative.
Into the derivative, which kind of sucks. But here we go. I'm plugging in a -1. That's a -8, -4, -5. I believe that numerator is negative. I just did it in my head pretty quickly. I plugged in a -1. The numerator is negative. Let me say something about the denominator. No matter what it is, the quantity is squared. If that denominator is squared, the denominator is always positive. So I got a negative over a positive. I think this came out negative. This whole region is negative. The function's decreasing. Let's try something in here. +1. Let's try a +1. A +1. That's -8 + 4 -5. I think that's negative. And the denominator's positive, so that's negative. So it's decreasing. Let's pick something way out here. 3 or 4 or 5, or I'll pick a 3. The denominator's positive. We said that 6 times. The denominator's positive, but I got to plug a 3 into that numerator, which kind of sucks. It's -72 + 12. Damn, I think that's negative. That wasn't too hard. It's pretty largely negative. Are you guys okay? This is interesting. We already knew there was no mins and maxes, but because of these asymptotes, they totally split this graph up into these 3 different pieces. It could have, it could have increased and decreased. I mean, it could have increased. It could have, but it didn't. This guy's decreasing always. I don't really want to do a second derivative, and I don't really want to look at concavity and inflection points. Maybe I should, though. Maybe I should. It's a hard work, though. Watch this. I wonder if you can go over here and figure this out. Watch this. If we go over here to this graph, watch this. With these asymptotes like this, and again, this makes you have to recall your pre-calculus and college algebra days a little bit. I mean, you got to remember what rational functions sort of look like. When you do have horizontal and vertical asymptotes, your graph approaches those asymptotes. They're not just there for the hell of it. Your graph uses them, and they act as a guide for your graph. So listen, when you're on the left side of 0, according to this, you're decreasing. I'm telling you, there's only one way. With these asymptotes like this, there's only one way for me to decrease. And it's like this. I mean, there is no other way to get around it. With asymptotes that act like that, with these asymptotes in this picture and the knowledge that we're decreasing, I swear to God, that's the only option. I mean, you might, with these asymptotes like this, you might think this is another option, but guess what? That's not decreasing, is it? That's increasing. So it's not that option. You might think, oh, well, if it's decreasing, it's doing this. Yeah, but no. I mean, this asymptote is here because this graph's going to approach it. So it's really got to be this. It's got to be that. Let's skip the middle for just a second. Let's go over here on the right side of 5/2. On the right side of 5/2, it's got a vertical asymptote, it's got a horizontal asymptote, and according to this, it's decreasing. I swear, there's only one thing to do. If your graph lives over here with all these asymptotes and you're going to decrease, there's only one way to do it. I think it's this. Do you agree? It's got to approach this asymptote. It's going to approach this horizontal asymptote. I guess you can't approach it from the bottom, or it would be called decreasing. sorry. If it's approaching it from the bottom, that would be called increasing, and we're not doing that. We are decreasing. It has to be that picture. That's pretty cool. Hey, by the way, I guess if we would have investigated concavity, we would have learned that this is concave down and this is concave up. I guess. It would have been. I didn't really need concavity to draw those shapes. With asymptotes, I know how the shape works with asymptotes. But horizontal asymptotes only act like, maybe I have this discussion with students all the time. I can't remember if we've had this discussion, but listen, you never cross a vertical asymptote because it's a place of undefinedness. You can't cross a vertical asymptote. But horizontal asymptotes are different. So you can cross horizontal asymptotes. You can. But you don't cross them when you head toward infinity. When you head out this way, you don't cross them. Then they really do act like asymptotes. But in the middle, they may or may not act like asymptotes. So you may cross the horizontal asymptote. It's perfectly fine. It's a different type of asymptote than an undefined vertical asymptote. It's different. So in the middle here, what was going on in the middle here? Between 0 and 5/2, we were decreasing. I want to say this. It's got to decrease. It probably approaches that asymptote. It's got to decrease. It probably crosses the horizontal asymptote. Let's go back to the original function a second. Can you tell me the x-intercept of the original function? The x-intercept is when it equals 0. A function equals 0 when the numerator equals 0. When does that numerator equal 0? X equals 1/4. You see that? Again, I haven't done much of this last week, right? What was I doing last week? I was taking derivatives and looking for critical numbers and inflection points. Now, I'm this week, maybe not the whole week, but so far today, I'm stopping and I'm analyzing the function itself for a minute. I'm looking at all the damn asymptotes, and now I'm asking you about the x-intercept. I'm analyzing the function a little bit, besides analyzing the derivative. I'm analyzing the original function just a little bit. X equals 1/4 is the x-intercept. You know, I sort of, anyway, I sort of missed that, I guess, when I drew it. 1/4 would be about right here. So maybe this graph is a little more accurate if I come down here. But it still probably has to, it probably has to change concavity in order to do this, in order to approach this asymptote. So you know what? There probably is an inflection point in here somewhere. You see that? I have to come down here. I have to live in that middle. I have to decrease from one asymptote to another. I probably have to switch concavity a little bit. Somewhere in there, there's an inflection point where you switch concavity. I know that's kind of new to us, inflection points. I'm trying to get you to see them. Do you see one there? You see what I mean? When I draw that kind of shape, there's a subtle change in concavity somewhere, right? You see that? It's concave up, and then it switches to concave down. I haven't even done a second derivative yet. I still don't want to. I'm doing avoidance behavior. Can you tell when you do avoidance behavior? I'm pretty darn happy. But if I asked you for the mins and the maxes, what would you say? Please list all the relative mins. There are none. And by the way, they would have been revealed here if there would have been any, but remember, there was no critical numbers, so there was no mins, and you can look at the picture and sort of verify that. And there are no maxes. There are no maxes. There might be an inflection point, I keep saying. I think there is an inflection point. But one thing that's new, what's new today is asymptotes. And these asymptotes sort of guide the graph, and they affect they affect this stuff about critical numbers and inflection points. I mean, that gets affected by these asymptotes. Yes, Carlos?
You said that there were no critical numbers for this derivative.
That's right.
But what was the reason for them going to the number one again?
What was the reason for what?
What was the reason they put it to the number one?
I didn't hear that last part. What was the reason? What?
The number one.
Oh, the number line. What about it?
Why were they tested on the number one first?
Oh, well, right. There was no critical numbers, but I did put these guys on the number line. What? And these guys are not critical numbers. What are they? What are they?
They're isotopes.
Yeah, they're my vertical asymptotes. So I put them on the number line, even though they're not critical numbers. And why? Because I said so. Yeah. That's part of the reason. Do what I say, not what I do. And this is new, right? Last week I didn't do this because last week I never had any dang asymptotes. Last week I never had any asymptotes, so I never did do this. But now I'm putting vertical asymptotes on my number line to test around them. And my reasoning is, I know they're not critical numbers, I know they're not, but they do something. They naturally bust the graph. They naturally split the graph into three pieces. And I want to investigate the increasing and decreasingness of these three pieces. So asymptotes are undefined places that split the graph into pieces. I need them on my number line. I need to test around them. As well as, if I had some critical numbers, they would be on here too, and I'd have to test around them. But I'm testing around these, and I know they're not mins and maxes, and I know they're not even called critical numbers technically, but I need them on my number line. I need them. We should do more with asymptotes. I might be finished with this problem unless does somebody really want me to do a second derivative? Or maybe you'd rather not. Just like me, you're avoiding it. I understand. I mean, it's not that fun, is it? I'll try it. Here, I'm going to try it. Anyway, what do I expect to find? I'm expecting to find some kind of inflection point between 0 and 5/2. I think there is one in there. That's what my graph sort of says. All right, on your mark, get set, go. What am I doing? Second derivative. All right, well, here's the first derivative. All right, you ready? Derivative of the first. Negative 16x plus 4. That's easy. Derivative of the top. Times the bottom. Okay, well, 2x squared minus 5x, the whole thing squared. That's the bottom. Minus, right down the top. Oh, great. Oh, my goodness. Oh, it's painful. Oh, I'm moaning. All right, and now the derivative of the bottom. You bring the 2 down. Oh, my goodness. And then that thing is 2x squared minus 5x to the first. You following me? You bring the 2 down. And then you got to do the derivative inside. This is multiplied right here, if you don't mind. 4x minus 5. I couldn't stick it on the end there. It's right here. All over the denominator squared, which is that denominator to the fourth. Hey, you can cancel a 2x squared minus 5x now. You can cancel a 2x squared minus 5x right now. Over here, do you see one? Actually, you see 2 of them, don't you see them? I'm going to cancel one. Over here, do you see one? There's one. I'm going to cancel it. And that means, because I'm canceling it there and there, I'm allowed to cancel it here. All right, that helped a little. Oh my God, if I really wanted to clean this up, I got to FOIL this numerator? You guys are crazy.
At least it's not squared.
And you got to FOIL all this? I really want to give up. I am too far to give up, huh? You're right. I'm like Indiana Jones. I'm hanging halfway down the cliff. I can't give up. You're right. All right. Negative 32x cubed. I'm distributing this. Positive 80x squared plus 8x squared. Did I do this right? Help me out. Help me. Negative 20x. Okay. I just foiled that out. Now I got to foil this out. See this? And, oh my God, it's got a 2. It's got this, and a negative sign. I'm going to foil it all out. You ready? Hey, that's another negative 32x cubed. But it's actually times 2. So it's negative 64x cubed. But it's not negative because that'll make it positive 64x cubed. Wow. Here comes a positive 40x squared. No, it's 80x squared. And I'm sorry, but it's negative 80x squared. Okay, I'm done with him. Here comes the 4x. That's a 16x squared. No, it's not. It's a 32x squared, and it's negative. Negative 32x squared. Here comes a negative 20x. Wait a minute. It's a negative 40x. No, wait a minute. It's a positive 40x. Well, this is funner than I thought. Here comes a positive 25. No. Here comes a negative 20x. But wait a minute. It's negative 40x. But that negative sign makes it positive 40x. I think I had a couple of those. Here comes a positive 25. It's actually a positive 50. No, it's actually a negative 50. Wow. I think I did that right, you guys. I hope I did. This makes for a real exciting video, too. Wait till later. You'll get to rewind this. Anyway, gather your like terms together. You see any, I see a 32x cubed. If I add these together. Any x squareds? These are gone. But I get a negative, oh no, and here's this guy. Negative 24x squared. Anything else? What about my x's? There's 80 minus 20, a positive 60x, and then what else? A negative 50? Wow, that's my numerator. Hey, what am I doing? What the heck? Are you lost? This is my second derivative, and it's done, and it's cleaned up, and I'm very proud of myself. When does it equal 0? When the numerator equals 0. That's kind of a battle. That takes me back to pre-calculus. So this numerator equals 0 is a cubic polynomial. I might have to try synthetic division or something. I mean, you know what I mean? I mean, cubic polynomials never were friendly. I mean, they're hard to solve, cubic polynomials. Quadratics are beautiful. You got a quadratic formula. By the way, cubics have a cubic formula. Have you ever seen the cubic formula? It's about this long. There's a cubic formula, like a quadratic formula. There is one. Nobody knows it. I mean, nobody has it memorized. It's too long. Well, I'm looking for my critical number. I knew there was one. I already knew there was one. I knew there was one. And there it is. It's whatever makes that numerator 0. It might not be pretty. It might be like the little cube root of something. It might be a nasty little number. It might not be a 1 or a 2 or a 1.5. You with me? It might not be that pretty. How would you, I want to know when this numerator equals 0. Let's see, what could you do? Could you divide out a 2? If you divide everything by 2, you get 16x cubed, 12x squared, 30x, and then 25. I just divided the whole thing by 2. I could try synthetic division. You know what I'd really like to try? Somebody, do you know how to solve this? Without, using technology. Do you know how to solve this using technology? You could graph this. It's a cubic polynomial. When does it equal 0 will be whenever it crosses the x-axis, right? Yeah. That's how you solve things when you get lazy. You can pick up your graphing calculator and try to find out when this equals 0. And really, it might be necessary because you may not be able to solve this by hand. It's a cubic polynomial. It may not be a nice answer.
0.812.
Really? So you found, and is there more than one answer, or is that it? How'd you find that?
I graphed it and found a root.
She graphed it and found the root. And even though it's a cubic polynomial, on her graph it looks like this. But the cubic part might be somewhere else. I mean, it's a steep cubic polynomial. She found, but on this steep part, she found where it equals 0. Where did she say it equals 0?
0.812.
All right, well, that's my inflection point. Hang on, where does that happen over here? Where does that happen over here? What was this point here? Do you remember this x-intercept?
1/4.
That was 1/4 or 0.25. So the 0.81 is about right over here. Yeah, if that's a 1, 0.81 is right here. Hey, look at that. That's my inflection point at that 0.81, I guess. Wow, amazing. All right, now what I probably should have done, so what did I do? I walked in here this morning and I wanted to do something with asymptotes, right? So I made up a problem and we did it. If I wanted the problem to be nicer, I would have spent all weekend working up a nicer problem. When you walk in on Monday morning and make up a problem, it ain't always too nice. This was not all that nice, was it? But if it ain't nice, is it a waste of time or did we learn some stuff? We might have learned some stuff. I mean, that's what's kind of nice about not nice problems. When they're not nice, they reveal a lot of interesting things. I really wanted to talk about the asymptotes, which was 45 minutes ago. Yes, Carlos?
I was there when you were taking this second derivative and you were canceling out the constant 2x squared minus 5x is. I say you have a square and you have a singular in the numerator and you have a fourth in the denominator, but how is it that you're able to cancel out the one as well and the denominator just becomes cubed instead of square?
Yeah, I just canceled one. Sorry, there's one here. I canceled one of these and left me one. I canceled one of these. I canceled one of these. I canceled one of these.
But how were you able to cancel the one that was over there at the end that has that's right so first?
Yeah, because it's the same as the denominator.
But how are they exactly the same if they have different degrees?
Right. Well, I canceled yeah. It's the base that I'm canceling. There's one of these, there's four of these, there's two of these. There's one of these, four of these, and two of these, and I canceled one. So now there's none of those, there's one of these and three of these. Yeah, it's like having an x squared, an x, and an x to the fourth. I canceled one of those, I canceled one of those, and I canceled one of those. Yeah.
But how is it that you're able to cancel the one that has the square, but yet that doesn't cause the denominator to go down an extra degree?
I didn't cancel two of them, I canceled one of them. Just one of them.
But how do you cancel one of them without altering the denominator's degree?
I did, I canceled one of them. I canceled one of them.
But you said you canceled one from where you have raised to the first.
Right, that's how you do it. You cancel one of them. That's how you do it.
But when you cancel one,
I want to look at, let's look at another problem. F of x equals, here's another one, you guys. This is better. This is a little better. Look at this guy. I want to know the vertical asymptotes. Hang on. I want to change it. I want to change it to 4x squared in the numerator. Sorry, the numerator is 4x squared, the denominator is x squared plus 1. I want to know the vertical asymptotes, and I want to know the horizontal asymptotes. So this is the new thing today. I wanted to come in here and talk about asymptotes. I spent 45 minutes on one problem. Here comes another one. This will go quicker. I'd like to know about the asymptotes. I need to take a 2-minute break.
Is this for a full body?
Yeah, so I'm sort of into 4 or 5 if I'm talking about asymptotes.